Welcome back to The Explainer. So today we're diving into a concept that honestly completely turned the physics world upside down. For decades, we all thought of black holes as the universe's ultimate vacuum cleaners, right? Like these cosmic traps so insanely powerful that absolutely nothing could ever escape them. But back in 1974, Stephen Hawking had this brilliantly massive realization that literally broke all the rules. He found out that these terrifying gravitational monsters, yeah, they aren't actually permanent. In fact, they are slowly but inevitably dissolving into nothingness. It really is the ultimate cosmic mystery. Are black holes truly the point of no return? Well, I want you to completely rethink everything you know about the finality of black holes. Because if we look closely enough, and I mean looking at the very fabric of reality itself, we find that these dark abysses actually have a slow, steady leak. And to understand how that's even possible, we have to look at this massive clash between the two most successful theories in all of modern physics.
Okay, let's dive into this. To understand how a black hole leaks, you have to picture a showdown between two foundational sets of rules. On one side, you have Albert Einstein's general relativity. In this classical view, gravity is just this smooth, continuous warping of space-time. You cross the boundary of a black hole, and bam, you're caught in a trap where not even light can get out. It's just completely dark. But if you apply the strange, microscopic, jittery rules of quantum mechanics to that exact same boundary, which is exactly what Stephen Hawking did in '74, the whole picture totally changes. Hawking mathematically proved that black holes aren't entirely black. They actually glow, just ever so slightly, and emit a steady stream of particles. But that begs the question, where exactly are these particles coming from if the black hole itself is supposed to be totally empty?
Right, so to answer that, we need to zoom way in, down from the massive scale of collapsing stars, straight into the microscopic quantum foam. You know, we tend to think of the vacuum of space as just empty nothingness, a total void. But quantum field theory tells us the complete opposite. The quantum vacuum is actually this highly dynamic, boiling soup. It's constantly fluctuating with these fleeting virtual particle and antiparticle pairs. Basically, these pairs borrow energy from the universe's accounting department, pop into existence for a tiny fraction of a second, and then, boom, they instantly crash back together to balance the books and annihilate each other. This is happening everywhere, all the time, completely unnoticed. Now, what's really interesting about this slide is seeing what happens when that bubbling quantum soup hits the edge of a black hole. Right at the event horizon, that ultimate point of no return, the curvature of space-time is just so extreme that it creates massive tidal forces. And those extreme gravitational gradients, they totally disrupt the normal behavior of the quantum vacuum. So instead of just letting those virtual particle pairs quietly recombine like they usually do, the black hole physically interrupts this little microscopic dance. Picture this. These virtual partners pop into existence, right there, literally straddling that event horizon boundary. The intense gravity acts like a giant wedge, violently ripping the pair apart before they even have a chance to annihilate. One particle gets sucked right across the horizon, lost forever down into the black hole. But the other particle, the one violently separated from its partner, is left stranded on the outside. Suddenly partnerless, it literally can't annihilate. So it's basically forced to become a real particle, and it just escapes out into the wider universe as radiation.
So the crucial point is that this is basically a bizarre three-step cosmic heist. First, you have these virtual pairs forming naturally in the quantum vacuum. Second, the extreme gravity at the event horizon violently separates them. And third, and honestly, this is where Hawking's math is just pure genius, to the outside universe, the particle that falls in appears to carry negative energy, while the escaping one has positive energy. It's this wild quantum tunneling mechanism. And that escaping positive energy? Yep, that is what we call Hawking radiation.
When we zoom back out to the macro level, the consequences of this are absolutely wild. By constantly eating that negative energy partner, the black hole is effectively having its mass bank account drained. Think back to Einstein's famous equation, E equals mc squared. It tells us that energy and mass are equivalent, right? So losing energy literally means losing mass. As the black hole shrinks, its temperature actually starts to rise. And as it gets hotter, it radiates even faster. It turns into this incredible runaway process that ultimately leads to the complete, total evaporation of the black hole in a final, violent flash of gamma rays.
But don't hold your breath waiting for it to happen. To really anchor the immense scale we're talking about here, consider a standard solar mass black hole. So one about the weight of our own sun. For that specific black hole to completely evaporate via Hawking radiation, it would take roughly 10 to the power of 67 years. That is a 1 followed by 67 zeros. To put that astronomical number into perspective, our entire universe is only about 13.8 billion years old. So yeah, if you were planning to sit back and watch a black hole vanish, you definitely want to bring a snack.
And what really blows my mind is that the story actually gets even stranger. Recent research coming out of Radboud University suggests this phenomenon isn't even exclusive to black holes. No way, right? They actually found that tidal forces in curved spacetime can separate these virtual particle pairs even without an event horizon. That means superdense objects like white dwarfs and neutron stars will also eventually evaporate through a similar kind of gravitational pair production. For a white dwarf, it'll take an unfathomable 10 to the power of 78 years, so it seems like literally everything in the universe might ultimately have an expiration date written right into the very fabric of gravity.
Now, you might be wondering, okay, if black holes are out there glowing, why haven't we ever just pointed a telescope at one and taken a picture of it? Well, it all comes down to basic cosmic static. The temperature of Hawking radiation for a solar mass black hole is just a teeny tiny fraction of a degree above absolute zero. Meanwhile, the baseline heat of the universe itself, the cosmic microwave background that's left over from the Big Bang, that sits at about 2.7 Kelvin. So our telescopes are completely swamped by this background heat. The black hole's glow is just way too cold and faint to ever detect against the loud static of the cosmos.
And this brilliantly illustrates one of the absolute greatest crises in all of modern physics, the black hole information paradox. You see, quantum mechanics demands this core rule called unitarity, which is a fancy way of saying that information about the universe can never, ever be permanently destroyed. But Hawking's math shows that this radiation is purely thermal. It's completely random. It carries absolutely zero information about the stuff that originally fell into the black hole. So, if the black hole evaporates completely into random heat, where does all that original information go? Relativity essentially says it's lost forever, while quantum mechanics says, hold on, that's impossible. It's a huge problem.
To actually solve this paradox, physicists desperately need a unified theory of quantum gravity. And recently, they've been playing around with a massive new mathematical tool called the double copy theory. Think of it like a cosmic Rosetta Stone. It essentially allows physicists to take the highly complex math describing tiny quantum particles and electromagnetic forces and translate it directly into the heavy language of massive black holes and general relativity. It's this incredible bridge, finally connecting the enormously huge with the unbelievably microscopic.
Let's move to and see how this builds, because this isn't just a fun theory. It's leading to real, tangible breakthroughs right now. By using this cosmic Rosetta Stone, scientists actually managed to map the mind-bending math of a collapsing black hole into a much, much simpler particle physics problem. Specifically, they translated it into a charged particle scattering off a collapsing shell of matter. By completely changing the language of the math and converting a dense gravity problem into a standard particle problem, physicists can calculate things that were literally impossible before. It's bringing us one massive step closer to figuring out exactly where all that lost information might be hiding.
Because at the end of the day, Hawking radiation isn't just some quirky little feature of black holes. It is the absolutely crucial intersection where quantum mechanics, thermodynamics, and general relativity all violently collide. It completely challenges our fundamental understanding of empty space, the nature of time, and the permanence of matter itself. So I'm going to leave you with this to ponder. Trillions upon trillions of years from now, when the very last black hole shrinks down to a microscopic point and explodes in a final flash of light, what ultimate secrets about the fabric of our universe will it finally reveal? Thanks so much for joining me on this explainer, and as always, keep questioning the cosmos.